Okay, shall we start, Pramod?
Yes,
Good
yes.
morning, everyone. Welcome to the plenary session of the 7th Indian Control Conference. My name is Vidyasagar. I am actually the general chair of this event. I hope people can hear me. Can someone just confirm that you can hear me all right?
Yes.
Okay,
Yes, sir, we can.
thank you. So this year has been a little bit challenging because of the pandemic and so on. In fact, the 7th ICC was supposed to have been last year in IIT Bombay, but everything simply got pushed back by 1 year. In any case, we thank everyone concerned for their cooperation in making things happen. In particular, this morning's plenary speaker, Professor Kargonkar, who is based in California and has very graciously agreed to stay up in the evening to deliver this lecture. Now, let me just deviate from the usual format of just reeling off degrees and awards while introducing the plenary speaker, if I may take that liberty. I have known Professor Kargonkar for more than 40 years. What happens is that many people become famous for doing high quality research after they finish their PhD. A small number become famous after their PhD for the work they did as PhD students. But very rare to find a person who was famous even while he was still a PhD student. And Pramod was certainly in that category. When he finished his bachelor's at IIT Bombay and went to work with Professor Rudy Coleman at Florida, already the controls community felt that this was someone that should be kept an eye on because he was going to do really outstanding research. So at that time, I was a professor at the University of Waterloo, and I invited Pramod to come and give a lecture while he was still a PhD student. I can't remember doing this for anybody else in all these. In all these years I've been a professor, I don't recall ever inviting someone to give a talk while they were still a PhD student. I'm not talking about job interviews, that's something else. I'm talking about an actual scientific seminar. So, in the early part of his career, Pramod worked on various topics in linear systems. His thesis was on linear systems over rings, and subsequently, he worked on what we today we'll call modern linear control, things like periodic control. In that phase of his career, the high point was undoubtedly the state space solution of the H infinity control problem, which is sometimes called the DGKF paper. Doyle, Glover, Kargonkar, and Francis.
Oh,
But towards the
sorry.
end of his contribution, what's happening here? My
Dr.
voice
Sagar,
is
your
very
voice is
faint.
very
Well, all
faint.
right. I'll bring it much closer if I can. Okay, can you hear me better now?
No, I'm afraid not. Your voice is really very faint.
How about now? Can you hear me better now? Okay, then let me switch to a different microphone. Can you hear me any better now?
Yeah, this seems better, yes.
Okay, so this is, I was using the external microphone earlier, but I'm just using the microphone that comes with the earplugs. Okay, anyway, I will just, let me just start from the beginning. Probably people haven't heard, we haven't been pressed for time. So I was just saying that Pramod was quite famous even as a PhD, and I had invited him to Waterloo to give a lecture. And he talked about his thesis topic at the time, which was linear systems over rings. And subsequently, he made various contributions like periodic control of linear systems. But I would say that the high point of his that part of his career was when he was one of 4 people who solved the state space solution for H infinity control. This is called the DGKS paper, John Glover control for fancy. But after that phase, he moved on to the control of semiconductor processes, applying ideas for control theory to semiconductor manufacturing. And many people, especially the younger ones in the audience, won't remember that in the 1980s, the yield on semiconductor manufacturing was about 3%. If you made 100 wafers, 3 of them worked, and you had to throw away 97%. Which incidentally meant that you had to test every single chip before you could accept it. So that was not very easy. The work of people like Pramod went a long way in creating today what we call the fabless foundry, where the process of manufacture is decoupled from the process of design. And then subsequently he worked on the control of power grid, though emphasis was on the US power grid. The ideas are much more universal. And now in his current phase, he is working on CyberPhysical systems, which is the topic of today's lecture. Another point I would like to highlight is that apart from having been a researcher in his life, Pramod has also been an administrator. He started off as the head of department at the University of Michigan, then became Dean of Engineering at the University of Florida. Then he became the assistant director of the National Science Foundation. Now, some of you may think that assistant director is like assistant professor. Let me assure you it's not. The assistant director, in the case of Pramod, had a budget of close to $1 billion. And after finishing that stint, he moved to the University of California at Irvine as the Vice Chancellor for Research. And if you have been keeping track of how many top-notch controls people have been moving to UCI, like Deepak Jeffrey and Magnus Augustine, you would know that the personal appeal and magnificence of Pramod has been a major factor in inducing all these people. So without any further delay, let me just say that Pramod will give his lecture on cognitive cyber-physical systems, vision and ideas for exploring the new frontier. Over to you, Pramod.
Thank you, Professor Vidyasagar. Can you hear me okay?
Yeah, yours is also a little faint. I wonder if there is some setting that the organizers have to change so that we can all hear better.
Yeah, I could hear you.
Okay.
Now we can also hear you. Yeah, go ahead.
Okay. So, well, first of all, thank you for inviting me to give this plenary talk. Let me just, your introduction was very flattering, but I regard Professor Vidyasagar as a role model that I have always looked up to all my life, and I will continue to look up to him for the rest of my career and life. And he's been a lifelong mentor and a friend and a family friend to us. So we very, very much appreciate the relationship that I have had with him and his family. So it's a special joy to be giving this talk. It's also great to be speaking at Indian Control Conference, being a product of IIT Bombay. And I know that IIT Bombay is hosting this event, and would have been even better if I was there in person in Powai to give this talk. So be that as it may, I'm going to speak to you today about some ideas that I'm calling cognitive cyber-physical systems. So the outline of my talk is I'll begin with some context setting and vision, spend some time describing this concept of cognitive cyber-physical systems, then talk a little bit about some technical directions that could be pursued in this context, spend a part of my time describing one paper, one recent paper, and then conclude. Before I go further, let me say that this slide deck has numerous hyperlinks in blue. So if you click on any of those hyperlinks, you will go to an article or some paper or some additional material that I would very much encourage you to go and look up for self-study. And I would love if you get interested to correspond with me by email or whatever works. I'm going to put my slide deck on my website, so you can go and find it. And I will also send to the organizers if they want to make it available to the audience. So this talk is dedicated to a friend, a mutual friend actually of Professor Vidyasagar and myself, Kishan Baheti, who was a long-time program officer at the National Science Foundation, lifelong friend. We worked together. He recently passed away due to COVID. And the work that I'm going to present today actually is supported in part by a grant that he was responsible for giving me when I became a professor at UC Irvine. So it's with some fondness that I dedicate this talk to his memory. So one of the questions that sort of animates me, and I think about a lot, is what if Wiener and people from that era were alive today? Think Shannon, Wiener, all the people involved in creation of cybernetics. I put the picture of his book along with a hyperlink to the PDF of that book. The title of the book was Control and Communication in the Animal and the Machine. And whereas cybernetics didn't quite succeed, it spawned off a whole bunch of areas, including control theory, as in the aftermath of cybernetics. The other thing it did was a series of conferences called the Macy conferences, and I've also put a hyperlink to Macy conferences. These started in mid-40s and they continued for several years. Wiener there brought together, of course, people from engineering, but also from psychology, from biology, neuroscience, mathematicians, of course, and anthropologists, to essentially think about this question of control and communication in the animal and the machine. Of course, he was driven by the context of the day. So, a lot of emphasis on feedback and automatic control. Because of Shannon, ideas from information theory were beginning to seep in. AI and machine learning were still not there. That would be a few more years after that, but the foundations were being laid. And so the question that hypothetical question that I ask is, what if all these luminaries, the founders of the field, if they were alive and they were witnessing what's going on in our world, what would they think about the future of CPS? What would they think are the big research directions? And what I'm proposing to talk about today are sort of my initial pretense to be anything close to that genius, but it's something that we can all think about together. So in case you have never heard of cyber-physical systems, this is a depiction taken from National Science Foundation of what cyber-physical systems are. So what they are, so there's the scientific core as well as an application sectors. In the scientific core, of course, you have control, but you have safety, you have verification, design, networking, privacy, IoT, real-time systems, data analytics. And then you take this core set of science and engineering and apply it to various application domains, such as manufacturing, agriculture, civil, materials, smart and connected communities, aero, automotive, energy. And so on the right-hand side, so those application domains are depicted in a little bit more detail. So for example, in transportation, you can think about manned and unmanned vehicles, connected and autonomous vehicles, improved airspace, in energy and automation, grid, for example, which is something that I work on, healthcare and biomedical, critical infrastructure. So these are all examples of cyber-physical system applications where we take the core techniques from cyber-physical systems and apply it to these domains. What are their properties? So pervasive computation, sensing and control, networked at multiple scales, spatial and temporal, dynamically reorganizing and reconfiguring. So as the system changes, the entire structure of information, computation and control changes. High degrees of automation, and I'll say a little bit more about this because at one extreme you have sort of self-driving cars or unmanned air vehicles completely on their own versus engineered systems where humans still play a significant role. So degree of automation depends on the application. A big premium on dependability of the operation with potential requirements for high assurances of reliability, safety, security, and usability because you're dealing with physical systems. So it's not like Microsoft Windows. So if it freezes, you do a reboot, but you really don't want to be doing things like that for these cyber-physical systems. So safety, security, usability are very important. With and without human interaction and supervision. Conventional and unconventional substrates and platforms. So here what is meant is it could be standard sort of computing and networking and control that we are aware of, but you could also take on very different kinds of substrates and platforms, both on the physical side as well as on the computing side. And they can range from very small, so from the nanoscale all the way to the planet scale, like the electric grid or the climate system. And these are all examples of cyber-physical systems. So in this context, what we are witnessing now in a very big way are what I'm calling smart X, where you can put for X anything that you like. So take, for example, old manufacturing, something that we've been doing for at least 100 years, going back to Henry Ford and beforehand. And what people are now thinking is, how can we make this manufacturing process smart? Similarly with electric grid, again, something that's been around for at least 100 years, if not longer. Again, ideas and visions and aspirations of how we can make the grid smart. Same thing with transportation, again, infrastructure that's been around for a long, long time. Cities which have been here for, hundreds of years, if not longer. Health systems. And you want to make every one of these smart. And I will say what is meant by smart, but it's certainly something as a prefix that's used to express an idea that these systems will get much more intelligent, if you will, or much smarter in terms of use of data and information in the future. And then autonomous systems, which are related to these systems, but here the autonomy plays a big role. So unmanned air vehicles, which are certainly now commonplace, still they're controlled from ground by an operator, but sometimes, particularly in space applications, you can have completely autonomous operation. Self-driving cars, certainly level 5 would be fully autonomous. We are not there and we may not get there for a while. Autonomous robots are a similar example of autonomous systems. So smart and autonomous are not the same things. I think there is a difference. And there is almost like a spectrum where you can go from smart all the way to autonomous. Clearly for autonomy, you are going to need a lot of smart, but smart doesn't have to be autonomous. One other point about these application examples, particularly those that have connection to humans and society, human individual and group behavior and their interactions with technological systems are central in many of these applications. That is how people, both as individuals and also in terms of organizations or groups, interact with these systems makes a huge difference. And you can see that in everything. And just think transportation system, right? So as we put more sensors and control and make, let's say, signaling smarter, people will react to that change and they will change their behavior. So you have to take that into account in almost every one of these applications. So what that leads to is the idea of smart cyber-physical human systems. So you want these systems that have a physical component, they have a cyber component, they have humans, and they are smart in terms of delivering services to people. So conceptually, you can think of this smart X in this diagram. So X, you can say, is your application domain. So think manufacturing, transport, energy. And then you have component technologies or component science like sensors, communications, Internet of Things, automation, data analytics, machine learning and AI, control and decisions. Those are the things that we are very interested in. Software architectures, how you implement these in software. Increasingly, cybersecurity plays a huge role in these systems. And then where you do the computing, you can go all the way to the edge, to the cloud. And there is enormous interest in apportioning the computing burden in this cloud to edge continuum. So you take some collection of these technologies, you impinge them on X on a question that's of interest. So that's what I think all these systems are trying to do in their evolution towards becoming so-called smart. So that's, I think, what has been at the back of my mind is like, how can we think about these things in a much more systematic and potentially exciting way, which can lead to new research agendas. And I'm going to now talk about this concept of cognitive cyber-physical systems as one way to think about these emerging smart X systems. So before I introduce cognitive cyber-physical systems, I want to give you a little bit of background about how to think about cognition, because that is going to play a central role in what I'm going to speak of. So this diagram, or this three-level analysis of is due to David Marr, who was a very, very talented computer scientist. He was a vision researcher who died relatively young. And he came up with this idea of three levels of analysis. And he said that any system, any cognitive system, can be described at three levels. Let me begin at the top. So at the top level, you might want to describe it by its goal or function. So you can say, well, I want to have vision. So vision is a function that you want a system to have. And you can describe that vision by saying, I want to be able to see scenes, and I want to be able to track moving images. And you can describe the goal or function in a variety of ways. And that you can describe perhaps in a computational description. Then you can say, okay, that's my goal, or that's what I want to do. How would I create an algorithm that achieves that goal or function? So you might have like a camera that's producing pixels, and then you want to do object detection. So you might come up with an architecture, an algorithm for solving that functional problem related to vision. And then third level would be implementation. So you come up with an algorithm and architecture. Where will you implement it? So like, for technological system, we'll probably implement it on CMOS computing, or maybe, in the future, maybe on a quantum computer or some other form. But you could also implement it in neurons. So he said that this description can also apply equally well to human cognition. So the implementation is in our brain through neurons. Algorithm and architecture are neurons of neuronal firing or signals and computation that the neurons perform through their connections. And that would be the algorithm, and the architecture of the connectivity of the neurons and how they talk to each other, and the firings and all that would go in the algorithm and architecture. And then at the highest level, you can look at different parts of the brain and say, okay, what function are they doing? So, this part is doing language recognition, this part is doing vision, this part is doing problem solving. And so he had this way of thinking about this three-level architecture, and this will play a significant role as I go about explaining the cognitive cyber-physical systems. I put a link to his really groundbreaking work. Cognitive science has a long history, but there was a sea change. It's called the cognitive revolution in 1967. And Neisser was one of the people who really transformed cognitive psychology and led to what we now call cognitive science. And he had a very succinct definition, which I very much like, of cognition. And he says cognition is all processes by which the sensory input is transformed, reduced, elaborated, stored, recovered, and used. And so I think, you can sort of easily understand what is being said here in terms of what cognition is. Now, I should say that for human cognition, which is really what inspires a lot of our thinking, evolution plays a huge role. So, because of our evolutionary past and because of genes that go from parents to children, and that leads to the brain of the infant that he or she is born with, evolution has played a huge role in our cognitive function. So it goes from genomes to brains to minds to cultures. And culture now plays a huge role in terms of evolution of our cognition. So in the last, let's say, 10,000 years, culture has begun to play a big role. This is not without controversy. There's a lot of very interesting thinking that goes on in the role of these evolutionary processes. So I put a link to a very nice paper that kind of can bring you up to date on how people are thinking about how cognition has evolved in human beings. But you can think of salient cognitive functions that we all can recognize: perception, we perceive the world, we pay attention, we remember things, clearly a cognitive function, and you can see that fitting into nicer definition very nicely. Reasoning, we reason about things. Problem solving, that's something that humans do really well. And knowledge representation, we represent knowledge that we have acquired over thousands of years, including our own lifetime. So, and this is not a complete list by any means. There are many other cognitive functions that one can think about. Okay, so with this background, this is my working definition. This is all sort of initial thinking, subject to modification as my own thinking matures. So working definition is that CPS are cyber-physical systems that have cognitive functions and capabilities. Okay, so we are thinking of engineered systems, including humans, which have physical component, cyber component, networks, control, machine learning, AI, but they are designed, they have these cognitive functions like the ones I described in the previous view graph. Now, CPS can be explicitly designed to have these cognitive functions, or they can learn or evolve to possess them. So we take no position as to which way it should be. Maybe you start with some design, but you also make them evolvable so that they can acquire these functions through learning. What specific cognitive functions and capabilities you want will depend on the problem setting. So it depends on what problem you're trying to, so that's the X part of smart X, like what's the problem you're trying to look at, that will dictate what cognitive functions you want to pay attention to. Cognitive CPSs in their sort of future may learn from each other. So you can imagine hundreds, thousands, millions of these cognitive cyber-physical systems that are talking to each other, learning from each other. They're learning from humans, and they're also forming collaborative networks. Cognitive CPS may be better able to augment humans and lead to human flourishing. So there is one of the big worries with all this stuff is, will it really help society and human beings, or will it cause harm? And I think if we equip them with this cognitive CPS framework, we might be able to design and evolve them in a way that they actually help humans rather than be against human interest. Okay, so this is my hypothesis, and this is really the sort of punchline of the talk, is this cognitive CPS concept that I'm proposing offers the most expansive and ambitious vision and program for integrating machine learning and AI with cyber-physical human systems to make these smart tech systems possible. So what I think can happen over the next 10, 15, 20, 30 years is that actually all those smart things that I showed you will become smart, and they will integrate machine learning and AI in its current form and its future form, and enable these CPSs to have these cognitive capabilities, which will improve over time. So that is what is sort of the vision for cognitive CPS. I will talk a little bit now about some of the technical underpinnings. So first, I want to remark on computational intelligence, because that's going to be a big part of anything of the kind that I've talked about. And there are two fundamentally different perspectives on learning from data. So one is simply statistical pattern recognition from data for prediction and control. So you have a bunch of labeled data or any kind of data, and you don't worry about what's underlying it. You simply try to look for patterns, and that's been the big success story. And we'll talk a lot more about that. But they can also go a different way, which is use prior knowledge and data to build causal models to understand, predict, and control. It's a substantially different way of doing things, which is to go through the modeling process. And it's certainly not the case that they are mutually exclusive. I mean, these are just two different ways of thinking. Currently, the first way of thinking is dominant, but as you will see as I describe the picture, that there is a role for models in this process. And let me just make one comment, because this is absolutely critical for the kind of applications we have in mind, and that is causality. So if you just take the pure pattern recognition approach, it's really not that easy to include causality. It's not impossible, it's not easy to bring in causality to make sure that it's not just correlation that you are learning, but you're really learning X causes Y. And I've hyperlinked a very nice paper, again, that can bring you the current state of the art in terms of how we can incorporate causality in learning from data. There is a whole field called cognitive computational neuroscience that we can draw from as we think about this cognitive CPSS. And there is a very nice review paper that I've hyperlinked at the bottom of this chart. And there is a very nice figure in this paper that I think speaks volumes, which is why I've included here. So on the x-axis is biological fidelity, on the y-axis is cognitive fidelity. So biological fidelity says, your cognitive model, how closely does it mimic the brain? I mean, what happens in our brain. So take the very classic Hodgkin-Huxley fourth order differential equation model of a single neuron. That is still one of the most accurate model for a biological neuron. Extremely high biological fidelity, because it really does represent firing of a neuron, but has nothing to say about how we do these cognitive things, right? Blue Brain project, which is really a project to connect, billions of neurons with this Hodgkin-Huxley models, has much higher level of biological fidelity, but even today, it really doesn't give you the cognitive fidelity that we would like to see in those models. And then on the y-axis, you have cognitive models, and I'll describe them a little bit more detail in the next slide, which are extremely close to how we humans think, but really have no connection to the brain. I mean, have no connection to how our brain is structured and how the neurons are connected and so forth. And now they have everything in between. So you have like deep neural networks, very, very important class of modern machine learning methods. So, it has some biological fidelity and a much higher cognitive fidelity. And then you have recurrent DNA and so what I think is happening in cognitive computational neuroscience is people are moving to the top right of the diagram, where you have very high biological fidelity and very high cognitive fidelity. We are not there yet, but this is where all these models are going to evolve over the next 10, 15, 20 years. The previous chart had some of this embedded in it, but I want to now make it much more explicit. There has been an ongoing debate since the founding of artificial intelligence about the nature of human cognition and the structure of the brain. So what's the relationship between the structure of the brain and how we have all these cognitive capacities? And this is the key topic, whether we do symbolic thinking or whether it's really just a connected bunch of neurons connected in each other and the symbols just arise. So it's a key topic in neuroscience, machine learning and AI, psychology, linguistics, and so on and so forth. So there are three major components to this. One is computational logic systems. So if you think of just very simple cognitive, some very simple reasoning, which is just first order logic. So those are very simple articulation of the symbolic nature of human cognition. And then you have this connectionist deep neural network models like deep neural networks or recurrent neural networks and so on and so forth. And then in either case, you have to have models and tools for uncertainty, because we have to deal with a great deal of uncertainty in cognition in terms of processing information from the real world with all the uncertainties in it. And so how do we deal with this uncertainty? So these are three pieces that put together are important for human cognition. I take I really have no position in this debate. I think it's a very important debate and we need to pay a lot of attention to it. I put a very nice recent survey paper on neural symbolic reasoning, a survey and interpretation, 2017. I think as far as I'm concerned, we should combine connectionist, logic, and probabilistic approaches to achieve desired system goals and objectives. So that's what we are going to do. So the first class of cognitive models go back to the work of, at least to work of Herbert Simon and Alan Newell. If-then rules, logic, symbols, goals and sub-goals, conflict resolution mechanisms. So there's a whole body of literature around on AI that was driven by these production systems. And there are like state-of-the-art production systems, ACT-R and SOAR, which are currently the sort of best such production systems created using the computational logic approach. Second kind of class cognitive models are reinforcement learning based models. So here one represents the agent in terms of action, states, and rewards. You might have perception and motor modules for the agent, value and policy based approaches in reinforcement learning. And then from sort of the latest neuroscience and cognitive science, there are three modes that one can see based on research in neuro and cognitive science: a model-free reinforcement learning, a model-based reinforcement learning, and episodic reinforcement learning. I'll say a little bit more about episodic learning in the future, so I'm not going to say much here. It is known, or it is certainly posited based on lots of experimental evidence, that our brain combines all these three modes. We know that our brain has model-free RL, model-based RL, and episodic RL, and it combines these three depending on the cognitive task that's at hand, but we don't really know how it does it. And I think as we discover how brain does it, we could take inspiration from that and put it in our cognitive cyber-physical systems. And then there are the Bayesian probabilistic models, very classical models to deal with uncertainty in cognitive models. One final word on sort of the big picture from neuroscience and cognitive science as to how people, what's the latest in terms of thinking about human cognition. So there is something called the free energy principle. It's an overarching unifying principle. And the reason I want to talk about it is because it is very close to control and the way we think. So it's due to Carl Friston, who is one of the preeminent neuroscientists in the world. And this particular thing is not the free energy principle, is part of it, that the brain seeks to minimize surprise. So brain operates in the real world to minimize surprise. It goes under the name of Bayesian brain hypothesis. Brain has an internal model that allows for computation of state estimate from sensory observations using Bayes' rule. Agent, that is the human, in our case, it's the human. Agent chooses action policy to maximize information gain, KL divergence or relative entropy. And the free energy principle then states that the brain minimizes expected free energy under future observations and future states. Okay, so this is what is meant by saying that brain seeks to minimize surprise. Friston, in his voluminous work on this topic, has mathematically formalized this, and he's got hierarchical models for doing this, both forward processing and backward processing as to how the brain does it through its multiple layers. And it's just a beautiful theory of how the brain operates. It's the most powerful, single most powerful theory that is out there right now to explain human cognitive behavior. And there's deep connections to statistical mechanics, predictive coding, risk-sensitive control. So there are really good deep connections here. Okay, with this background, I'm going to now talk about some of these cognitive properties. So first in machine learning and then in cyber-physical systems. So perception. Arguably, this is where machine learning has really revolutionized in the last 10, 15 years. So it's perception. And the great thing about deep learning is that compositionality, it's just built into the structure just because it's a composition of layers. So compositionality of learning is built in, and extremely impressive progress in computer vision, speech recognition and processing, language translation. And what are the architectures? Convolutional neural networks that you can really show how they are connected to how our brain processes visual images. LSTMs for recurrent neural networks, and transformers. I'll say a little bit more about transformers in a future slide. So how might we have perception in cyber-physical systems? So clearly, cyber-physical systems with multiple distributed sources of sensed information. So just think of any one of those examples with a bunch of sensors which may be distributed. And what you would want to have is that cyber-physical systems to be able to perceive through those sensors what's happening. And this immediately allowed us to leverage deep learning advances. So as soon as you have camera sensors in your machine learning system, so you can think of manufacturing as an example where use of cameras is ubiquitous. Now, in case of cyber-physical systems, as in machine learning, prior knowledge plays a huge role to make sense of what is being seen. Because without prior knowledge, you can have completely nonsensical inference about what you are seeing. So neural network techniques like deep learning could be combined with relational prior knowledge for improved context awareness in sensor-rich CPS, because you can't afford to make a mistake. And there are nice tools that are becoming available to combine, say, deep learning with these relational prior knowledge, like neural networks with symbolic front ends. So you have a standard deep learning network, and you have a front end that does sort of this computational logic type of front end, or inductive biases, deep learning, and graph networks. So there's a very nice paper that combines graph networks to encode the relational prior knowledge and gives the bias for the machine learning system. And then there are explicitly relational neural networks. That is, in the structure of the neural network, you have built these relations that the objects in the real world obey. So all these things could be leveraged for perception. Second sort of major theme, certainly in machine learning, and I think it's going to be very important in cognitive cyber-physical systems, is attention. So vision has been a major focus for modeling of attention. In fact, one of the things that human beings do a fantastic job of knowing what to pay attention to, because we are bombarded by so much sensory information that through all that clutter, we know what to pay attention to. And it's a huge capability that humans have. And I think cyber-physical systems with rich sensors are going to need to have these kinds of attention capabilities. I just put some links to theories of attention, but mostly in vision. So there is something called the feature integration theory, a contour description theory of visual attention, signal detection theory, very classical sort of statistical signal processing kind of theory. And there are computational models for attention, Bayesian models, decision theoretic models. There is a very nice survey paper that I have linked here where you can go and look at in much more detail these models of attention. In machine learning, attention has played a huge role and just explosive growth. So in fact, attention is the key to focusing on the most relevant information from multiple distributed sources of information. Transformer, which is sort of the heart of latest revolution in natural language processing, is an example where the structure has a bunch of attention blocks, as you can see on the right-hand side. And there is a sequence of papers going to 2014, where by incorporating attention into these either deep or recurrent neural networks, they were able to make substantially faster progress in solving these problems, whether that's on vision or language translation. So like the second paper, effective approaches to attention-based neural machine translation. So accuracy of language translation improved dramatically once attention was brought into the network. And there's a very nice paper, Attention is All You Need by Vaswani et al. That has this transformer. And then it's also been used in generative adversarial networks. I think attention is hugely important in cyber-physical systems, again, because of the sensor-rich system. What should the system be paying attention to? So we have some initial thoughts. You can think of two levels of attention. First level would be selection and focus on a particular task. And second level would be top-down search for relevant information. And you could use this for detecting changing conditions and contexts, for fault detection and resilience, because you want to react to fault condition, attention would play a huge role. And hierarchical and programmable models will be very important for cyber-physical systems. So there are a couple of examples, the transformer that I just showed you, and non-local neural networks, which can be programmed to give attention. And so they can be used as tools for building an attention in cyber-physical systems. Third cognitive capability I want to talk about is memory. Clearly, memory is central to learning and intelligent behavior. In fact, if you know anybody with Alzheimer's, you will recognize the truth of what I'm saying. There are multiple memory mechanisms in human cognition. Again, there's a huge body of literature. Nobel Prizes have been given for memory, like Eric Kandel. There is the short-term memory, long-term memory, episodic memory. We remember episodes, and then semantic memory. So LSTM, the long-term memory, is a great example of use of memory in machine learning. Experience replay, a key innovation in deep RL, deep reinforcement learning, was an example of use of memory for improved training of reinforcement learning. I'll talk about differentiable neural computer in a second, and sparse distributed representations. In fact, we have used hierarchical temporal memory in one of our applications. I'll speak about that at that point. So this is really very interesting paper. And what they did, this is a paper of Graves et al. About 4 years ago. They took a standard neural deep learning network, which is on the left, as you can see, recurrent network. And then they have an external memory and read, write, storage, retrieval operations. And what they show is that by taking a recurrent neural network, and by appending this dynamic external memory, you can improve the performance of the system significantly. And so this was sort of an example where you took kind of latest machine learning models and append to them an external memory. This is another recent paper, which again, it's a different implementation of a similar idea. So they have this something called the Maxcell cell, memory attention and composition cell, which has a control, read and write head. And this unit is replicated multiple times over to create a learning system that has built-in memory. So control unit, read unit, write unit. So to taken together, these compositional attention networks for machine reasoning are created. Now, in case of CPS, one thing that I think has tremendous possibilities is episodic control. So the idea of episodic control is to reenact successful episodes from memory storage. Every one of us, knows how to ride a bike. We learned it a long time ago when I was, say, maybe 8-year-old or 10-year-old. I haven't ridden a bike in like 30 years, but you give me a bike and I will recall all that and use it in my current setting. So we know that the brain does this. There is this evidence. And I think it's going to be extremely powerful for learning from small data. That is, if you don't have enough data or for real-time action, episodic control can play a big role. There is a nice paper, Model-Free Episodic Control by Blundell et al. That I have linked. You use recorded experiences that are used as value function estimators. Neural episodic control is a similar idea, but you combine deep learning model with lookup tables for action values, and hierarchical episodic control, where episodes are used as options. So instead of having an action, you have the entire episode as an option. Okay, those are examples. What are some of the big challenges? So there are at least four big challenges that I think are ahead of us. Approaches for combining model-based and model-free techniques. Approaches to combine hierarchical and distributed architectures and algorithms. Reducing the need for large amounts of data. Few shot learning, one shot learning, can we bring all of that kind of thing to cyber-physical systems? And bringing meta-learning paradigm into cognitive CPS, learning to learn. So I will say a little bit more about each of these. So this is, in a way, probably the one area that I think is most amenable to immediate progress. So one approach could be you use model-free approaches for sensing, perception, memory, and model-based approach for planning, safety, and closing the loop. Because model-free is really suitable for perception tasks and memory tasks and sensing tasks. And you really need to have some model in order to assure some level of safety. So that could be one way. Model predictive control and reinforcement learning. So compute action sequences based on model via NPC, update the model via reinforcement learning and supervised learning. So this is another different way of combining model-free and model-based. And then there is a nice paper which is, I think, a very, very interesting advance on this combining, which is you take local linear models and learn robust local policies, and then you stitch them together using model-free methods to guide a global policy. Hierarchical control, I think there hasn't been as much progress as we really need. So this is a big open area. Clearly, for the kind of complicated systems that I talked about, we are going to need hierarchical structures because it's just too complicated to be managed by a single controller. So we're going to need some kind of a hierarchy to manage the system. There are some beautiful papers in psychology, cognitive science, and machine learning. So there is this nice paper of optimal behavioral hierarchy where they talk about how humans decompose tasks. And in fact, they have an idea of optimal decomposition, optimal hierarchy of tasks. So there is a task, there are subtasks and the whole structure. And what does it mean to have an optimal hierarchy? It's a very nice formulation of that optimal hierarchy. Clearly, hierarchical control is going to be a natural framework for compositional learning. And there is very nice initial work on learning at multiple scales in time and space. I don't have the time to go into detail. You can click on those links. Okay, in the last few minutes, I want to talk about some recent work that we have been doing. So first, just like a big picture. So we have worked on external memory for adaptive control. We have worked on online learning and optimization, reinforcement learning for matching markets, online meta learning, some applications to smart grid and manufacturing, and some very recent work on building empathy. So in memory and pre-adaptation, we have some papers that take standard neural network adaptive controllers and append an external memory. And then we show read, write, retrieve operations and how they can improve the performance of the, and then we also have attention models in neural adaptive control. We also have papers on pre-adaptation in adaptive control. Let me skip past that. Lots of paper on online learning and optimization. So regret guarantees for online learning and control, online disturbance gain minimization, extension of H infinity problem to online learning, adaptive gradient online control, matching algorithms. We have done some work on reinforcement learning for matching markets in smart grids and shown that it has the potential for having scalability for these matching problems. So again, I'm just going to, and then we have done some applications. I want to spend the remaining few minutes talking about meta learning and one specific result so that you can get a flavor for the kind of things that we are working on. So meta learning, which is learning to learn efficiently and effectively, I think is a key characteristic of human beings. This is, in fact, this is what college is supposed to be all about, is we teach you how to learn. This is something that we teach kids, and I think systems will need to have this learning to learn. This idea has been in machine learning world at least since the mid-80s, and it's very common in nature and humans. It's a very nice paper that I've hyperlinked on meta learning in nature and humans. And there are two possible approaches, at least two. First is to learn common structures across tasks and induce a strong prior or inductive bias through Bayesian inference. So in the first approach, you have a bunch of different tasks that you want to learn how to learn, and then you use Bayesian inference. So there is a very nice mathematical theory that goes along the first line. And the second approach, which is computationally more tractable, is a two-level optimization framework. An inner optimization optimizes for the task at hand, and an outer loop that optimizes parameters for the inner optimization. So the outer loop is learning to learn, and the inner loop is learning. And so we have done a recent paper on this. I'll just explain that. So we imagine a situation where there are n episodes, each of length t. In each episode, the environment draws an arbitrary AB pair from a set of AB pairs. And within each episode, it's standard linear dynamics with state measurements in noise. There is a cost function at time t, and cost function for the future may not be known. So we have some uncertainty about the cost function in the future. Information at time t is a preview of the cost for the next some number of periods and past y and past u. The dynamic regret is a fairly standard definition. So you have the cost function for a given algorithm, and then you have the optimum, and the difference between the two is the regret compared to the optimum with complete information. So CI star is the optimum, and the average regret is just the sum of regrets over n episodes. Okay, so the final result is a guarantee on this average regret. So what's the architecture of this meta learner? So the outer loop is going to create, so take theta star, and its output is this phi hat, which acts as a bias on the inner learners. I will show the equations in a second, and then the inner loop learns in real time the system. So for the inner learner, you have a standard loss function, in terms of estimation error. Then you have least squares estimate of loss function plus a bias. And that bias, as you can see, comes from the outer learner. So the phi hat is the bias, and the term RE, in addition to the squared error, taken together, biases the estimate towards phi hat. The outer learner produces phi hat. And so here it's over tasks. So each task is indexed by I. Theta star I is the best learner estimate for episode I. The loss per episode is theta star I minus phi hat, Frobenius norm. And then you have a gradient algorithm and a gradient and projection to update phi. So you first update phi I hat through a gradient step and then do a projection step to get the next bias, phi I hat plus 1. Control policy is receding horizon control. So you have this preview for next m steps, and you essentially do receding horizon control. So you find the optimal sequence for the next m steps, but apply only the first instance and then repeat the computation. So it's a standard RHC formula. And then because we need to learn, there has to be some balance of exploration excitation. So we apply a perturbation in addition to the optimal input or computed input. We apply a delta U to give some persistence of excitation condition with O of square root Tk, and this specific rate of growth balances exploration and exploitation. So then,
within each episode, you have a bunch of intervals given by this preview length, and then you update the estimate of the theta hat from from interval to interval until you come to an end. And within each interval, you apply the receding horizon control policy along with the perturbation. And the main result, which we think is nice mathematical result, is we can set under some suitable technical condition with probability greater than 1 minus O of delta, this average regret goes down as square root of n, plus a constant A star and a term that depends on the length of the episode. But the main point is this 1 over square root n dependence. So if for sufficiently large number of episodes, this R bar will converge to this lower bound. So dynamic regret guarantee with limited preview. This is the main contribution of this paper, and then a bunch of other. So these are publications that we have. Again, you can go and read them. I want to bring this talk to an end and then maybe do some question and answer. So I have presented cognitive cyber-physical systems as a vision for the next frontier in CPS. I think we have just taken the most elementary steps. I can see research in this going on for the next 15, 20, 30 years. It's so rich. It's such a rich idea that we can keep going. They can provide a framework for integrating machine learning and AI into CPS so that it's more conceptual than just let's slap some deep learning into some controls. I think I find that attractive. Architectures and algorithms inspired from computational neuron cognitive science have great potential for cognitive CPS. Deep learning is just one example of a neuro-inspired machine learning technique. I think there is so much more that we can do to make progress. And I think they can enable smart tech systems for societal benefits. So with that, I thank you for being here. And I thank Professor Vidyasagar for inviting me to give this talk. And I'll stop and take any questions.
Yeah, can I just ask whether people can hear me this time or no? Okay, good. So thank you very much, Pramod. That was a wonderful talk, very panoramic sweep of the emerging field of cognitive cyber-physical system. I do agree with you that this field is going to be active for many, many years. Now, people are welcome to type in their questions either in the Q&A box or in the chat box, and I'll kind of keep track of them. But while I'm waiting for people to type in their question, let me just ask a philosophical question. Your last set of slides, where you talked about a bound for online regret minimization for receding horizon control. It's a very nice result, no question about it. But in this broad field of cyber-physical systems, how receptive are people to these kinds of mathematical results?
Yeah, it's a great question. I think this sort of theoretical research is to lay the foundations and conceptual foundations as well as mathematical foundations. But in sort of practical terms, people care about the impact you have on the application question. So you have to kind of connect all the way to the application.
So I have a selfish
In short, there is limited appeal for purely theoretical results. I mean, we do it because I think it's important to lay these foundations for the future so that it's not all completely ad hoc. And like I said, I think this is just scratching the surface. I think there are going to be interesting such mathematical questions that also go towards applications.
Yeah, I have a selfish motive in asking that question because I should tell the audience that Professor Kargolkar gave a wonderful short course at IIT Mandi. Sanjay Bhatt was there, I was there. And that was actually what inspired me to start exploring this field of reinforcement learning. And I'm now trying to put together a set of notes with the title Reinforcement Learning via Stochastic Approximation. That title may change eventually. And there I find that the pendulum has been swinging back and forth in the sense that 30 years ago, people would just take some learning algorithm, simulate it a few times, publish some results and not bother about it again. Now I find that even the so-called practitioners are a little bit more sympathetic to the theoretical foundations. Now, what I mean by sympathetic is they don't mind if you have to make a few simplifications in order for the theory to apply, but it at least gives them the confidence that the ideas are not totally crazy. In other words, proof by simulation, which was probably a completely mainstream idea 10, 15 years ago, I think is being complemented by some semblance of a rigorous mathematical proof. That's my impression, and I wanted to know your reaction to that impression.
I think RL in particular is very much amenable to what you are saying, mainly because there is this deep connection between RL and Bellman dynamic programming, and so there is this history of the connection between RL and big fundamental theory in control. I think it's a little bit harder in deep learning. I mean, there are a lot of people working on the mathematical foundations of deep learning as well, but the progress there is perhaps a little bit slower than RL. Although we know that RL is very slow. I mean, I think the real problem with RL is that it is extremely slow in the real world, which is where I I was going with some of my commentaries that by taking into account how the brain does it, perhaps we can find faster ways of doing RL. I mean, RL systems that actually work in the real world.
Do you think RL systems are slow because we insist on provably convergent algorithms?
I don't think so. I think it's, to me, it's algorithmic improvements that is coming up with smarter ways of doing RL. So perhaps it will have narrower domain of applicability, but it will be faster. Or including priors, or including some additional components to make otherwise RL will be very hard to use in the real world because of it's very, very slow learning.
Yeah, I don't really quite know why that is, whether it's because the algorithms are bad or because this whole paradigm of Markov decision processes or linear control is too restrictive. I don't particularly know. I mean, there don't seem to be any questions, so let me just indulge in a bit more speculation. If I go back about 30 years to when I first came back to India and set up the Center for AI and Robotics, the emphasis back in those days was on provably correct inference algorithm. And the logic that was given is that if you throw 1,000 hypotheses and 1,000,000 rules at a machine and the machine spews out some answer, you wanted to be sure that those rules and that set of observations really did lead to the conclusion. Otherwise, what is the use of automating everything? But even back then, it was known that human beings don't think logically. What I mean by logically in the context of formal logic, we think semi-logically, coupled with some sort of a BS detector. I mean, if the answer that comes out of the program is complete nonsense, we have a way of recognizing that. So, and all this talk about fuzzy logic and all that was an attempt to capture the second part, which I'm calling as the BS detector in a machine. I don't believe anyone has actually succeeded until now. So I mean, the part of your talk that I found very interesting was capturing the intuitive aspect and the human cognition aspect. So that's quite interesting. So I still don't see any questions in the chat box. So before I close the session, let me ask one last time whether are you planning to write a book or anything on this stuff?
I don't know. I think I'm interested in exploring more before I write a book. I think we are at a very early stage of this journey. So my hope is that some people in the audience will find it interesting and start digging in themselves and maybe develop some collaborations. That's nothing would please more than that.
But if you thought you were early, what do you think about Wiener in 1948? He had no results, only questions, right?
I know, but I'm no Wiener.
Well, no, that's a separate issue. I'm saying that some book which has almost no answers. But
that's true. I mean, cybernetic. Yeah. Oh, that way. I mean, I think the vision part is ready to be written. I mean, I'm pretty convinced of the vision that I'm promoting. And if that's what you mean, I think we are going to write some at least position papers. We have written one on cognitive manufacturing, but I want to do one on cognitive CPS, which lays out this whole program, like I explained in this talk, and maybe give some initial guidance on where the research could be done. But that's very much on my mind.
I think that will be very good, especially for the kind of young people who are in the audience. If there's a broad vision laid out, broad program, let me call it, they can work on bits and pieces, and that will become an integrated whole. Well, all right. I guess there are no further questions. So let me thank Pramod for staying up at night in California. We really appreciate it. You may want to note that the ICC 8 is going to be in IIT Madras the week after CDC, and we are planning it as an in-person meeting. So maybe we'll see you there.
Well, thank you for having me in this conference, and I'm going to make my slides available. So
yeah, please do that. You can mail them to me, and I can make sure that they get up on the.
And then I will put them on my website as well. So thank you very much, and have a wonderful conference.
Thank you. Bye, Papa.